you should probably consider this example more to the beginning, kind of a plug for the topics course that I am going to try to run, not in the spring, but in the fall. Actually, it's kind of funny. My first PhD student many, many years ago, I taught like a number theory class, and I put this question on one of the homeworks. And this student of mine was very kind of rabidly anti-calculator. This was back in the day when there were arguments over whether you should allow graphing calculators to be used in the calculus class. And he was a leader of the banner, carrying the flag about the calculators ought to all be put into, into the garbage can kind of thing. And he got really angry about this because he said, and now I'm in like a graduate level topics course, and I had to use a calculator in the course. Right. So you'll see. So find an element in z adjoined with square root of -89 that has an irreducible factorization of length 2. That's not so hard to find. And another one of length 12. Now, I'm going to kind of use some facts that we've talked about a little bit, and I'll try to explain them as we go along the way. But, oh, by the way, let me point out that this is a Dedekind domain, because if you remember that we had that earlier theorem that says the ring of integers of a quadratic ring of integers, or the quadratic ring of integers, is z adjoined with the square root of d, if d is equivalent to 2 or 3 mod 4, and it's z adjoined with 1 plus radical d over 2 if d is equivalent to 1 mod 4. Well, -89 is equivalent to 3 mod 4, and so this is the full ring of integers. Right, so this is a Dedekind domain. And it turns out, so I'm going to call it ring R, just because I'm lazy. And here's part of the sort of plug of, what I hope to be offering in the fall is I'm going to tell you how you can figure this out, right? But it turns out that the class group of this, I know that for any Dedekind domain, that the class group is finite abelian group, and in this case, it turns out to be the cyclic group of order 12. Right? Can anybody tell me why it is that the existence of an irreducible factorization of length 2 and another of length 12 is assured? And in fact, this is sort of a consequence of the way the Krull theorem works. Right? So, yes. Or
the class group is isomorphic to 12, and then it's going to have an element of order 2 and an element of order 12.
Okay.
And so those should really be related to yours.
Okay.
Right. You do kind of your same thing as you did before, where you take the element of order 12 and its inverse.
Okay. Right.
You can take the power.
Okay, so pick an ideal class of order 12 in there. And the order of phi function says there should be what, 4 of these, I guess. Yeah, I guess that's right, 1, 5, 7, and 11. Anyway, so there should be, there's a class of order 12 and select select a prime ideal P that lives in this ideal class. This means that P to the 12th is principal. But P to the K is not principal. Or any K that's snuggled between 0 and 12 proper. Right? So suppose that P to the 12 is equal to alpha, right? And now I'm going to do the trick that Grant told us about. Let Q be prime in the inverse classifier. So notice that Q12 equal beta, again, it's principal, behaves just like that, and so I have P to the 12, Q to the 12, and PQ all principal. And actually, I can throw in some more adjectives here. I like adjectives. What adjectives can I apply to alpha, beta, and gamma? They're all irreducible. We discussed this in the Krull theorem here, but think of it this way: if gamma broke down into X and Y, then X factors into prime ideals. If it's proper, it has to factor into a proper subset of these prime ideals, but both of these are non-principal, which is impossible. And you get the same kind of contradiction with alpha and beta when you realize that P to the 12th is the unique factorization, say, of alpha. If alpha equals XY, then X or Y, or well, just say X, has to be of the form, if it's a proper divisor, has to be in the form P to the K, where K is between 0 and 12 strictly, and it's impossible because that's not principal. So we're good to go. These are all irreducible. And notice that if you look at this is alpha beta. PQ to the 12. Therefore, there exists a unit in R. And by the way, let me point out the only units of this plus or minus 1, as a matter of fact, such that so 2 irreducibles here and 12 here. Now let me go just a step further on this. Let me go just a step further on this by saying that One. Oh, so it's gonna be 90. Let me check this. I think this will work. Of course, I don't know that's 90. That is a little suspicious. And notice. I get through there. I don't know if I get through there. I bet. Let's see. I'm just square that. That's a bit better. Well, I guess it should have worked anyway, because we've got 3 and 2, and just 1 minus, yeah, I guess it should work. So I think the P and Q should work here. Let's do what P times Q is. So thanks for it. 9 and. Oh, yeah, I see what it was. Notice PQ is generated by these, right? The square of 3, and then 3 times this guy, 3 times the conjugate guy, and then the product of this and its conjugate, which is 90, right? So notice again with our usual argument, 3 divides everything here, right? And notice this guy and this guy are in here, so their sum is in here. So you get 6 in here. So you've got 9 and 6, so you've got 3. So the containment works both ways, maybe fall. And so this is what we want. It turns out nobody wants to take 12 power of this ideal and try to assert that all the powers along the way are not principal. Of course, you only need the ones that divide 12. But there's another way to see it. So in this case, you can take P equals you can take Q to be its conjugate. Of course, it's clear that this is in the inverse class of this because the product of P and Q was in fact principal, right? And PQ so this is playing the role of our gamma, so PQ generated by 3. Anybody know what P to the 12th is? You can get on your horse and ride. I mean, basically, if this works, what happens is 3 to the 12 should decompose into P to the 12 times Q to the 12, right? And so basically those two should be conjugates. So look at 3 to the 12, which is 500,000, a little bit more than that, and exhaustively try to write that as a square plus 89 times a square. And actually, well, let me write it this way. And actually, I forget which is which. I may have them turned around. In other words, this might be q to the 12th, and this might be p to the 12th. I'd have to check that, but this is what it turns out to be. And if you multiply, so in other words, 640 squared plus 37 squared times 89 is the same thing as 3 to the 12. By the way, you can also prove that this ideal class has order 12 by running this argument in reverse and making sure that these are irreducible, right? They both have norms of 3 to the 12. Just go through and find everything of norm 3 to the k, where k is less than 12, prove that none of them divide it. So now you've got two irreducibles, and you can reverse engineer the argument and show that you've got an ideal class of order 12. Okay, any questions? Okay, so that's some fun stuff, actually. There's lots of really kind of cool combinatorial type arguments you can do in this. So we're now going to do a bit of a chapter on Noetherian rings. Noetherian rings are good rings because we looked at that most recently. We looked at this from the point of view of ascending chain of prime ideals, or I'm sorry, ascending chain of ideals. But of course, Noetherian means that every ideal is finitely generated. This is equivalent to every prime ideal being finitely generated. And when you want to do commutative algebra computations involved, or if you want some kind of algorithm to work, things like this, Noetherian rings are really the best playground in the world because every ideal is finitely generated, so you have this kind of finiteness condition that you can work with. I usually work with stuff that's a little bit more general, but there are some very nice theorems that you get from Noetherian rings. I am going to start by reviewing a couple of things, just to kind of make sure we're on the same page. So these first couple will be theorems of the same. As far as Noetherian, of course, you all know that my blanket assumption is every ring has an identity, but I have to emphasize this here a little bit just to make sure, because it's Converse of Gilmer's I like. Then this is another thing that makes Noetherian rings a nice playground. When you join a polynomial variable, you still get that all the ideals are finitely generated. The proof of this, most of the proofs that I've ever seen are kind of bulldozery. You do kind of what comes naturally, I think. But actually, in most proofs that you see, like in particular Dummett Foote and Hungerford, you see these kind of standard proofs, which I think I showed you as well. It's a little bit subtle where the fact that this uses an identity comes up, but it does because making no assumption about the identity in the beginning, if Rx is Noetherian, then R is Noetherian with identity. So in other words, if you have a ring without one, the polynomial ring is never, ever, which is kind of cool. All right. Here is another one. I'm going to just go on. Now I'm going to do power series case. Okay, suppose I have a prime ideal in a power series ring. and let P zero be the image of P and R under the homomorphism that takes it to zero. In R under a homomorphism P more power X into R given by P of X. So this is the homomorphism that basically, and let me give you kind of a word of caution here. This does not mean the constants that are contained in P. In fact, it's more than that. All the constants that are contained in P are in P naught for sure, but there may be other stuff, right? So for example, probably know at least from folklore that I've told you in this class that this thing is a UFD because it's PID power series. And if you look at the ideal, well, actually, let's just do this. We'll see if the ideal generated by that element. So I gave it a rather bold notation. I'm acting like it's prime. Leave I justify my bold notation. Well, let me ask you this. Let me first claim. I claim that generator that I put in there that seems to have the sequence of primes going higher power. I claim that's irreducible. How come? Right. Let's suppose, just for giggles, that you could factor this, right? So 2 plus whatever is some power series times another power series. What can you say about the constant terms of those other power series? The constant term of one of those power series has to be either 1 or -1, right? Because the constant terms will give a factorization of the constant term 2. 2 is an irreducible, in fact, it's a prime element of Z. That means one of the constant terms has to have a 1, right? And what happens in power series when you got a constant term of 1 or -1? It's in unit, right? So this thing is irreducible. Agreed? Okay, now we'll up the voltage. I now claim it's prime. It is a UFD, and so any irreducible is prime. So in fact, P is prime. If you look at P intersection, this is the 0. Right? Everybody okay with that? Or, I don't know, maybe I guess it could be 2, couldn't it? Or could it? Actually, would everybody agree that P intersect Z has to be either 2 or 0, right? Right, because really P intersect Z are all the constants in here. And let me point out, well, let me say it's either 0 or it's contained in the ideal term, right? Because what's the constant term in here, right? Well, the constant term is 2, right? So any constant term that's in there has to be a multiple of 2, right? Actually, might be a little more out. Yeah, I am curious now. So let's suppose. Can somebody tell me why? This can't be the ideal derivative too? Let's suppose, let me call this f of x just for short. What does that say about g of x? It has to be a unit, right? So this means right? So this means that f of x equals 2 times g inverse x. And let me just call this g hat of x. Which means that f of x has a factor of 2 in it, right? 2 has to divide every coefficient of f of x, and that's clearly not the case, right? I mean, it certainly divides the constant term, but it doesn't divide any other. Right? Now, how about something more? What if f of x times g of x equals 2k? Is that possible? Anybody got an idea on how to prove it?
In your, I want to say in the expansion of your product power series, K would have to be relatively prime to every prime.
Yeah, that's probably right. So if you have let's see what we have here. Let's say a0 plus a1x, say 2x squared. But actually, there's another argument you give. So I mean, I do like kind of getting my hands dirty, but there's another argument that you can give that has to do with prime ideals here. But let's see what happens here. This means that 2a0 equals 2k, correct? Has to happen, which means that a0 is k. Well, so now I've got that a little bit better. Let's look at the second coefficient. So now you have 2a1 plus 3k is equal to 0. Right? Which means that 2 divides k. Right? So now I know this is even, so maybe I can call this 2k prime. Or let's look at the next one here. 2a2 plus 2a2 plus 3a1 plus 10k prime is equal to 0. What can we conclude from that? Be a 4k prime? Maybe. 2 divides k. That was k. Yes, okay. No, I think it's fine.
So we're getting the 10 from.
Oh, when I was multiplying out. Yeah, that's probably right. So that should be it's 2a2 plus 3a1 plus 5, so that's 10k prime, right? Is that right? Is that okay? What does that mean about a1? A1 is even. And by the way, so is A0, right? This is even too. And I think you just keep going, because now you have 2A3 plus 3A2 plus 5A1 plus 7A0 and 0. This is even, this is even, and 2A3 is even, that means A2 is even, right? So in other words, every coefficient all coefficients are even, right? Or, I'm sorry, yeah, all coefficients are even, right? And so, yeah, so we can now reduce the problem here to K, so we can get this out here.
Yeah, divide by 2, and then 2 essentially has to divide K.
Yeah, that's right. That's right. So you can kind of tunnel that. And of course, from that, what you get is K is 0, and then you've got a problem. Another way that you can look at this actually is this is a prime ideal, all right? And so, are we in agreement about that? That P was a prime ideal. What do you know about its intersection? Its intersection has to be a prime ideal, right? And that's the more sophisticated observation is the intersection has to be a prime ideal. And it's readily apparent that one of the possibilities is 0 and the other one is 2. But we very easily show that 2 cannot be in this intersection. So let me get this right here. All right. And so P intersects Z with 0. However, the P0 in the theorem that I wrote up there in a race like an idiot, this is actually the ideal driven by 2. Because what you're doing here is you're nuking the X. So you're not just looking at constant terms in there, you're actually looking at constant terms that appear on any power series within that ideal. So two. P0 is P of P, where so this is your P0. Then P is finitely generated. If and only if then any ideal in power series, right, is finitely generated if and only if P0 is finitely generated. And we can be a little bit more specific. If P0 is generated by n elements, then P can be generated by n plus 1 in general. If P naught is if P naught is generated by n elements, then P can be generated by n plus 1 elements if X is in P and n elements, if X is not. We've actually gone over this, when we look back at power series before. Notice certainly that if P is finitely generated, certainly P0 is finitely generated. And if you remember, the way that we did this actually is, actually the case where X is in P is the easiest one. If X is in P and P0 is finitely generated, then what happens is just take these generators here and throw them in with X, and it's easy to see that anything in P can be written in that form. All right. On the other hand, if X is not in P, then how does this work? If X is not in P, then you pick, for every generator of P0 that you have, say A1 up to AN, you pick a power series in P that starts with A1 up to AN. And you show that that set actually generates the prime ideal. Prime is very important in this because you need, if X is not in P, you need X times whatever else is in P. And that's how you keep it going. We did kind of this proof. It actually requires a choice, as a matter of fact. So, as a corollary to this, let me give you a couple of corollaries. And this is a roundabout way of doing it. We've seen this corollary before, theorem probably. If R is Noetherian, so is R power X. And of course, I'm using something about Noetherian rings that I mentioned, but did not write down today. But how do you check that R is Noetherian? You only have to check the prime ideals, right? If all the prime ideals are finitely generated, then you're good to go. And this theorem covers it for you. You have any prime ideal. If R is Noetherian, then P0 is automatically, well, P is finitely generated if and only P0 is finitely generated. I don't know that P0 is a prime, but I do know that it is finitely generated ideal if R is Noetherian. And in any case, if P0 is generated by n elements, then P is generated by at most n plus 1. So all prime ideals in R power X are finitely generated. And so we're good to go there. Here's another one. I mentioned this, but probably didn't prove it, so now I can sketch a proof for you. If R is a PID, there's a rather famous example that shows that if you're a UFD, the power series ring does not necessarily have to be a UFD. However, I did mention that if R is a PID, then R power X is UFD. And actually, I'm only going to prove this, but you can actually extend this corollary to any finite number of variables. That is to say, if R is a PID, then R power X1 up to Xn is also a UFD, as it turns out. But just for the PID case, how do we do this? Well, let's sketch a proof of 604. Any ideas on how we would do this? Okay, so take your favorite PID and look at a prime ideal that's power series ring. Okay, now of course our goal is to show that that's a UFD. So what strategy, what tack should I take here, perhaps?
prime ideal.
Correct. So we need to show P contains a non-zero prime element. So let me take my caveat here. Let me be careful here and say, let P be a non-zero prime ideal. You sure it's non-zero prime element. Okay. So how do we do that? Yes.
We look at P naught, which will be prime in principle, and then it'll be generated by a prime element, which will have to be in our original.
Here's the problem. Here's the thing that's gonna make you cuss. Let me give you an example. Here's a good example. Yeah. This is prime, right? So. And the reason is I know that this is UFD. And so all I need is a status variable here. And this will be prime, right? And so you say, well, maybe this can factor. Right, maybe. But of course, the only non-trivial way you can have this factor is with a pair of twos or a pair of minus twos. And whether it's plus or minus doesn't matter. Right? Because the only other way goes 4, 1, making one of these unit, right? And you were dead in the water out the door because that gets you a 4. But now matching coefficients, you get x should be 2b1 plus 2a1 x. And that's problematic because the coefficient is odd on the left and even on the right. So here's the problem. This sucker is prime, but P0 is the ideal generated by 4. All right, so that's a little bit of a thorn in the side there. So how do we get around that? Well, if X happens to be in this prime ideal, then I'm done, right? If not, how about the stronger statement? What does the statement say? P can be generated by n plus 1 elements if X is in P. But if X is in P, there's no problem because there's your prime element. And n elements if X is not in P. But n is the number of generators that is needed down, whether it's a prime ideal or not. R is a PID, so P naught is generated by a single element. By one element as every ideal in R. So in particular, P naught is principal. Right? Therefore, there you go. Okay. So let me give you you this last thing. I don't know if I'm gonna have time to prove this before next time, but, this one, this is an important, theorem, and it's leading up to important stuff like Nakayama's lemma. How many of you have heard of that? Nakayama's lemma? Yeah, I kind of figured you would, yeah. So, make sure. 605. Well, it'll be a Noetherian, I an ideal, okay, so we've got an ordinary ideal of R, so it's got to be finitely generated then. A finitely generated R module. So I is an ordinary ideal, so it has to be finitely generated. A is an R module that is finitely generated, and B in A is a submodule. Let C be a submodule of A which contains IB. Which contains IB. Okay, and it's maximal with respect to the following property. That C intersect B is equal to IB. So C is just some submodule of A, which contains IB, and is maximal with respect to the product that C intersect B is exactly equal to IB. Then a large enough power of I times A must be inside of C. So this is actually going to be a useful bit of work, or something useful for us in the future. And we're going to use this. Yeah, so I'm not going to prove this yet. We'll go through that next time. But let me give you something along the spirit that uses this. There. Yeah. This is often called the Krull Intersection. So let R be the theorem. And I in R an ideal. And A finitely generated R module. A finitely generated R module. And B, the intersection this is of course of the natural numbers. Not negative integer. So R is Noetherian, I is an ideal in R, and A a finitely generated R module. if you let B be the intersection of all powers of I times A, you intersect all that. Then IB equals B, as a matter of fact. So we'll discuss this further next time and talk about why these are true. Any questions before we roll for today? Any questions? All right. Well, y'all have a good one, and we'll see you on Wednesday.